Dr. L. Jones Torsius Das, Professor of Mathematics, College of Engineering Gindi, Anna University, Chennai. He has obtained BSc and MSc Mathematics from Madurai Kamaraj University and PhD from Indian Institute of Technology, Bombay. He has served as NBHM Postdoctoral Fellow at Indian Institute of Technology, Bombay, and then as visiting faculty at University of Tennessee, Knoxville, USA, and Colorado School of Mines, Golden, USA. He is currently working as a professor in the Department of Mathematics at Anna University, Chennai. His research area includes numerical analysis of ordinary differential equations and partial differential equations. He has published more than 25 research papers in reputed international journals. He has visited many countries like USA, UK, Italy, Malaysia to participate in international conferences. He has completed DST SCRB funding project.
Welcome to UGC lecture series on computational mathematics, a practical laboratory course for BSc Electronics honors students. As a continuation of the lecture series, today we are going to see numerical differentiation and numerical integrations. Basically, numerical differentiation is an approximate method to find the derivative of a function. So, this is the derivative, first derivative of a function, okay. And by the definition of a derivative, it is basically the difference quotient. Difference quotient in the sense the difference between the function values to the parameter values. It is the ratio of difference between the function values to the parameter values, and in the limiting sense, this is the first principle for different derivative. And if you just remove the derivative, it will be in the approximate solution. Basically, it is the y difference upon the x difference, or the ratio of function difference to the argument difference, and you are calculating for small h values, then this will be very close to that derivative. This is the main principle behind numerical differentiation, and that is utilized in almost all the concept. The concentrating on the point x naught. So, from x naught you are locating another point to the right. So, you are going in the forward direction to the right side. That is why this difference scheme is called forward difference formula. That is basically, once again I will tell you, it is the ratio of function difference to the argument difference. Put it in the other sense, if you call y as f of x, it is y difference upon x difference. Again put it in the other sense, it is called del y upon del x, which is the approximate of the derivative. And mainly Taylor series is utilized to compute the numerical differentiation. For example, consider the Taylor series of a function f about a point x with the increment h, and that would be the function value f of x and h times the first derivative and h squared upon 2 times the second derivative. The f within the superscript 2 indicates the derivative, okay, at x, and hence you will get a higher derivative terms. Okay. Similarly, if I take this term, the first f of x term to the left side, it is basically the difference between f of x plus h minus f of x, which could be this term h into f derivative, h squared upon 2 into second derivative of f, and x squared upon 3 factorial into third derivative. So, this gives an approximate, if I divide by h and f of x plus h minus f of x upon h, this is the one which we saw in the previous slide. This is the forward difference scheme, and now we are giving actual definition using Taylor series, and this is the forward difference, and you have a derivative term, and these are the error terms. So, forward def derivative is defined to be this one, which will give you f derivative is equal to the forward difference, f difference upon ratio of f difference upon h x difference with the error term. Okay. So, this is an approximation to the derivative with a error order of h. Similarly, I can go with 1 forward to 2 forward. So, f of x plus 2h to equal to f of x, here h is replaced by 2h. So, in a similar way I get the derivative is equivalent to f of x plus 2h minus f of x upon 2h with this error term. This equation is 1 and this equation is 2. So, both equation will give the approximate value of the derivative of x at a point, and that here you have forward difference to 1 step, here forward difference with 2 step, and now multiply the first equation by 2 and then from that you subtract the second equation, we obtain this one. Once again that is equal to the f derivative with higher derivatives and again higher derivatives with h square order and h cube order. So, which will give you the same thing, and that will give you an error f prime is minus f of 2h f of x plus 2h plus 4 times f of x plus h minus 3 times f of x upon 2h. So, the derivative is approximated with the difference quotient. Difference quotient in the sense it is a quotient or ratio of function differences at consecutive points upon the argument difference. So, the first derivative can also be approximated with this, and which will give you a rule for the first derivative, and this is called the 3-point formula for the derivative, and the error term is given here. Similarly, the other 3-point formula for the first derivative. So, consider the Taylor series of f about x. You have f of x plus h, f of x plus h times first derivative plus h squared times the second derivative, the same Taylor series you have. And now take the Taylor series about f of x minus h. You have f of x minus h. How do we get from the previous one? Replace h by minus h, and you subtract these two equations. I get the function value at right point x plus h minus function value at the left point x minus h, that is 2 times h function value, the derivative value dx with the error term. Once again the same thing you have. Now, if I divide by 2h, from this equation divide by 2h, I can get the first derivative plus the error term is equal to this formula. Again, once again it is also the finest difference quotient, basically the ratio of difference of function values to the argument value. Here the function difference is taken as function value at the right point minus function value at the left point upon the difference length 2h, and this is called the central difference because the error is of h squared, and this is the central difference scheme for the first derivative, and it is called another second 3-point formula. X you have, and you have x plus h, and you have x minus h, and you have the difference quotient of function value to the argument value. So, you have the derivative. This is the approximate derivative value of the derivative of f. Function value, the derivative value of f at x is approximated by the function value at the right point minus function value at the center point upon the h, the length. This is called the forward difference formula, and this is the error term for that. And again this is the first 3-point formula for the derivative. That means the function value at x plus h and x plus 2h and x are evaluated in this fashion upon the total length. So, from x to x plus 2h you have 2h length, and this is the error term. And again third, the second 3-point formula, the derivative is approximated as the ratio of function value at x plus h, that is the right point, minus function value at x minus h, that is the function value at the left point, upon the total length. The length between x plus h and x minus h is 2h. This is the other formula for the first derivative, and you have the error of order of h squared. And now you take an example. We see that consider the function x times e raised to x. We would like to calculate the first derivative of x at 2 with h to be 0.1, and now around 2 I have taken 4 points, 1.9, 2.0, 2.1 and 2.2, and using the first formula, forward difference formula, I have f derivative value is equal to f of x naught plus h minus f naught f at x naught, that is x naught is 2, h is 0.1. So, function value at 2.1 minus function value at 2 divided by the difference, that is h. So, I get this derivative value. Similarly, using the first 3-point formula, so I have function value at x naught minus 3 times function value at x naught plus 4 times function value at x naught plus h minus function value at x naught plus 2h, and substituting here I get these 3 values. And using the second 3-point formula, function value to the right point, that is x naught plus h, minus function value at the left point, that is x naught minus h, take the difference, divide by the length 2h. So, I am getting this value. So, now you compare for the same function x e raised to x at the same point 2, I am calculating the derivative value using 3 difference, and this is the exact value is 22.167168, and you can see the numerical value of the derivative using first formula and the second formula and the third formula, and you can see that the error is minimized at the last formula, that is using the second 3-point formula. You can see that error is minimized. Now, we move on to computing the numerical values of second derivative. So far, we have discussed only the numerical value of the first derivative. Now, we are going to see the numerical value of the second derivative, and as usual we start with Taylor's series. In any numerical methods, without Taylor's series plays a crucial role. So, we follow that, we utilize the Taylor series of a function f around x with the increment x plus h. So, Taylor series is that knowing function value at x and higher derivative value x, you can compute the function value at neighboring point, and similarly to the left neighboring point you can compute, you can have another Taylor series, and now taking the difference or add these two equation, you can see that odd derivatives are getting cancelled. Here you have h plus h f derivative x, and you can see minus h f derivative. Similarly, look at the plus h cube by 3 factorial, the third derivative, here minus h cube. So, when I add these two will get cancelled, and finally, I end up with this. So, f of function value at the right point plus function value at the left point is 2 times function value at plus 2 h squared by 2. This is basically h squared, the second derivative. Now, bring the 2 f of x to the left side. So, I can have an order. You can see that right point, function value at right point minus 2 times function value at the midpoint plus function value at the left point. So, that is nothing but the h squared times the second derivative with the error term. So, now divide by h squared, you can see that in the previous equation, now divide by h squared, I am getting this. So, the second derivative is approximated with these difference quotient and this is the error. Second derivative is approximated, basically function value at the right point minus 2 times function value at the midpoint plus function value at the left point upon the h squared, the square of the increment. So, this is the approximation for the second derivative. As a part of this lecture series, we are going to see the next topic, the numerical integration. Here basically we are going to concentrate on computing the approximate value of the integral a to b f of x dx. Basically the definite integral of a function f of x over the interval a to b is basically, the geometric meaning of that is basically the area under the curve between x equal to a to b. So, this is the basic, the one of the geometric meaning of definite integral, and that we are going to utilize and exploit in our lecture. Suppose you have a function like this f of x, and this is the point x equal to a and x equal to b. We basically want to calculate the area enclosed by the red line, that is the graph, the curve area enclosed by the red line between x equal to a and x equal to b. Basically the area covered under the red line between the dotted lines x equal to a and another dotted line, that sometimes it is very difficult to calculate. So, what we go for, we are going to approximate that area by area covered by a regular polygon. Basically we are going to approximate with this regular polygon which is shaded blue. With a blue shade we are going to approximate. You can see that here you have excess area and there you have less area, that will compensate and which will give you an approximate value of that area. You see, once area is the value of the definite integral. So, by this we are approximating the definite integral, and basically the regular polygon is called a trapezium. So, we are computing the area of the trapezium. That becomes the area of the trapezium is function value at basically this length f of a plus this length. Take the average of these two lengths, that is f of a plus f of b by 2, then multiply by this length, the b minus a. So, the area of trapezium is calculated that the average of the left length height and the right height, f of a is the left height and f of b is the right height by 2, that will give you the average times the length, base length b minus a. So, the definite integral of a function, it is approximated by the area of the trapezium, and this is called trapezoidal rule of approximating the definite integral. And similarly I can go with 3 points x naught to a 2, and now the function is approximated with a second degree polynomial, and this is basically the second degree polynomial, and you integrate, and integrating this value and evaluating these small 3 integrals, I leave it to the students. It is very easy and simple computation, one can do it, and that will give you this formula, basically function value at the left point plus 4 times the function value at the middle point plus function value at the right point, that you add it and multiply by h by 3, that is called Simpson's 1/3 rule. So, basically you are integrating, you are computing the approximate value of the area by trapezoidal here, and next by Simpson's. Now, we go for, instead of having only 1 or 2 division, if the interval a b is divided continuously for n sub intervals, then you can have a better approximation, that is called the composite numerical integration. And you can see that the red line is the curve of the function f of x, which we would like to integrate it from where, from x equal to a to x equal to b, and this is the integral, and that integral instead of making that integral, that area that can be approximated with computing area of these smaller strips. You can see that these smaller strips are colored with different colors. Compute the area of smaller strips and then add it, you will get the area of the bigger portion, which is the area enclosed by the curve between x equal to a to x equal to b. And this is basically called the Riemann sum, and if you make infinitely make further division, which will coincide with the exact integral. So, you can also see in another example that the red line is the graph of our function, and now between a to b I divide the interval into 1, 2, 3, 4, 5, 6, 7, 8 sub intervals. The curve also divided into 8 rectangular strips, and basically I am choosing the left point rule. So, consider this rectangle. This rectangle is obtained by the function value at a, basically the left point of this interval, sub interval, and with this length. And here also, what is the left point? This is the first point. So, function, the rectangle is constructed with the length as the left point and width as the small sub interval length. So, likewise I am taking left interval, and I can calculate the area of the rectangle, which is nothing but length into breadth, and now I can add each piece which will give you an approximate value. You can see that here these portions it exceeded the actual area, but here it is not exceeding the actual area, in fact you have less areas. So, you can have a trade off like compensation here, but still the sum of area of these rectangles are only approximate value of the area enclosed by the curve between x equal to a and b, which will be the approximation of the definite integral. So, you have x1 a, x2 as the next point, a plus del x, and look at here f of xi del x. You take a ith variable here, f of xi is the length and del x is the small. For example, this it could be the ith point, f of xi is the length and del x is the width, and so the f of xi del x will give you the approximate, it will give you the area of these small rectangular pieces, and such as pieces, n pieces we are adding, we are summing, which will give you the sum of these rectangular pieces, and which is approximation of the area enclosed by f. So, area enclosed by f between a to, which is the definite integral a to b f of x dx, is the area enclosed by the graph y equal to f of x between x equal to a. So, now you can just see the previous one. When I calculate the area of the first rectangle, I will have the f value at a and f value at this point. Again, when I calculate the function value out here, the same point will also appear 2 times. Okay. So, this is the composite trapezoidal rule, and divide the interval a to b n sub intervals and apply the trapezoidal rule on each sub cases, and you have the following rule. You can just observe that the left end point of the interval a appears, the function value is evaluated at a plus the function value is evaluated at b, and in between points you have function evaluation of function 2 times it appears, and this is the composite trapezoidal rule. Now, we take an example. We are taking the function to be sin x and the interval is 0 to pi, and we are making 20 sub intervals. Okay. So, if the length is 0 to pi, which is the AB, and we are making 20 sub intervals. So, what will happen to the length of small sub intervals? That will be the length of that divided by number of sub intervals. So, you have pi upon 2x, and you have the points. When k equal to 0, you have x 0. So, x 0 is nothing but the left point 0. When k equal to 1, I have pi over 20, the first point, Likewise, I have 20 points. So there are total 21 points because 20 sub intervals, each interval will have 2 points. So there are 21 points, and I am evaluating function value at the left point f of a, that is sin 0, and function value at the right point b sin pi, and function value at the all the mid interval nodal points. I calculate and I sum it 2 times I am doing, and this is the numerical value of this integration. So, I will just explain the pseudocode for the composite trapezoidal rule. This is the pseudocode for composite trapezoidal rule. You can see that the input for this is a, the left end point, and b, the right end point of the interval over which we are integrating the function f, and n is the number of sub intervals. So, the inputs are a b interval and n the number of sub intervals, f of x function to be integrated, output the numerical value of the integral. So, here we calculate the length of the small sub intervals. How it is calculated? You take the length of the actual interval a b, that is b minus a, divided by n sub intervals, which will give you the length of each sub intervals. Now, I am just calculating the nodal values. How nodal value is calculated? When k equal to 0, it coincides with the left end. When k equal to 1, a plus h, which will be the nodal point x1, the first nodal point, a plus h. When k equal to 2, a plus 2h. Likewise, you just define the nodal values for n points. So, from 0 to n I get n plus 1 points. Now, the initial value of the integral, that is we have the f of a, the function value at the left point, and f of b, the function value at the right point. Now, for k equal to 1 to n, and for each into a k, I am just updating the sum with the prior value of sum. It is added 2 times f of k. So, 1 to n minus you will be having. So, this sum initially f of a plus f of b, and this will be what 2 times f of x1 plus 2 times f of x2 up to 2 times f of xn minus 1. You can just see that which coincides with f of a value and f of b value, 2 times function value at the inner points, in between points. So, that you can see that the original sum is f of a value and f of b, and in the block structure I am calculating for k equal to 1 to n minus 1, I am calculating 2 times the function value of the interpoints. That is added with the original sum, which will give you the trapezoid rule, and once you divide by h by 2, that gives the trapezoid rule. So, this is the numerical integration which we written at the end of the pseudocode. We move on to another numerical integration which is called composite Simpson's 1/3 rule. This is the composite Simpson's 1/3 rule. Basically, this should work for even number of sub intervals. So, instead of taking first interval, we are going to take first 2 intervals, and then we are going to next 2 intervals, and next 2. So, it should be even number of intervals. So, when you calculate the first 2 intervals and apply the Simpson's 1/3 rule, you have function value at the left point plus 4 times function value at the midpoint plus function values on the right point, and the right point will be the left point for next consecutive 2 intervals. So, that will appear 2 times. Therefore, you have odd number of points, odd number of nodal points are the midpoints of 2 consecutive intervals, and even number of points other than the first and last, that will be the end point of consecutive interval. So, that function value as that will appear 2 times, and the function value of this will appear 4 times. So, this is called the Simpson's 1/3 rule. One can easily verify. Again, I am going to take the same function with a even number of intervals 20, and I am going to, this is the usual way of computing the nodal values, okay, and I am just calculating sine at the left point, sine value at the right point, and sine value at even number of the nodal points it will appear 2 times, and sign value at the odd number of points that will appear 4 times. So, you calculate the sum of that function value at even number multiplied by 2, sum of function values at odd nodal points multiplied by 4, I am getting this. Okay. Let us see the pseudocode of the Simpson's 1/3 rule, and in fact we are going to discuss the pseudocode, basically the method, the algorithm for composite Simpson's 1/3 rule. What are the input for this? The input is the interval AB and n, the number of subintervals to be used in this, and here in this case n should be even. For Simpson's 1/3 rule, the condition is the n number of subintervals which you are going to use should be even, and f is the function to be integrated, and output is the numerical value of the integral. As usual, we calculate the length of each subinterval, that is the length of the actual total interval, bigger interval AB, by how many intervals you are using, number of subintervals. So, that will give you the length of each small interval. I am calculating the nodal values for k from 0 to n. If you use n subintervals, each subinterval have 2 n points. So, there will be n plus 1 nodal points. You are calculating a plus how many times it is located from the left side. So, that is, if it is k shift, you will have a plus kh. For example, k equal to 0, you have the left point. For example, k equal to n, I get the right point. For in between k equal to 1, I get the first point, a plus h, then a plus 2h, a plus 3h, up to a plus nh, which is nothing but the right point. And now sum indicates the numerical integration. Initialized, the sum is initialized the function value at the left point A, function values to the right point B. And now here there is a block structure for k equal to 1 to the last even points other than the right point. I am adding that 2 times, I am calculating the function value, and that is updated in the even sum. That will give you the even sum of that. Even sum is initialized to be 0. Similarly, you have odd sum. Odd sum is the function value evaluated at odd nodal points multiplied by 4, and that is updated with odd sum. Okay, and here odd sum to be initialized as 0. So, you are calculating the function value at odd integral points, odd nodal points, and finally the sum plus odd sum and even sum, that will give you, and summary. The main purpose of numerical integration is to compute the approximate value of the integrals, and based on the discrete data of the function we are doing, and the discrete data often occurs in many practical application. So, in this lecture we just discussed the composite trapezoidal rule and the composite Simpson's rule and the questions. Now, carefully you take these questions. The students are advised to do this. For this function 1 upon 1 plus x squared, you have to calculate the composite trapezoidal rule with 0.1 as the subinterval length. Same thing one should do it for the composite Simpson's rule, and compare with the exact solution. What is the antiderivative of 1 upon 1 plus x squared? It is tan inverse of x, and this evaluated with that tan inverse of x between 0 to 1, it will give you pi by 2. So, just there is the exact value, compare with that, and the students are instructed to write a computer program based on the pseudocode for this evaluation of numerical integration. So, I thank the students for patiently listening to my lecture, and in this lecture we have learnt the numerical differentiation techniques and numerical integration technique, and pseudocode of that 2 methods, and using that you can write code. Thank you very much.